Okay, let's get started. So I posted assignment 1 yesterday. Any questions about either the assignment or the lab or anything about the class? Yeah.
So for the lab, we didn't have comments or
For the labs, for the first few, you don't have to add comments because it's just basically getting used to working with the build system. And pretty much everyone's going to turn in the same assignment anyway. For the lab, they're going to turn the same thing in anyway because they're working with the TA and there's only a few changes you need to make. Plus, you're given a code skeleton, so don't worry about the first few labs about like readability type things. It's just in the future we may take off points if you don't provide comments to something that seems a little complicated. And we'll get to what types of comments are good and which ones are just completely useless. Because a lot of people here, some of my colleagues just say, put comments everywhere. And I disagree with that notion. Putting comments where they're useful is what is really important, but we're going to get to that. Other questions? Okay, so last time we were talking about a whole bunch of things, but namely these variable things, identifiers, what identifier names are okay for the things we want to work with. And then cin is where we stopped last time, which, well, what does cin do? Yeah, it gets input for us. So cout produces output, cin gives us input, which is nice. So let's go on to actual data. So we should try to at least understand if we're going to be storing data in the computer, what types of data are we allowed to store? And one of the most common ones that we'll be working with are integers. So if you want to hold a number that doesn't have a decimal, anything that's just a whole number, then an integer is probably the right data type for you. So there are two types of integers. So one is called a signed integer, and one of them is called an unsigned integer. Okay, so what's the difference? A signed integer is where you either the number is negative. Every negative number is signed by default, but if it's positive, it could be either signed or unsigned. So how do you tell the difference? Usually when you want to print something or work with an actual number, you put the plus to indicate that you want it to actually be signed. But if you just have like 12 here, then that doesn't have a sign on it. But even that's not actually enough for the language. So what you do is, instead of just saying int something, maybe int x equals 5, for example, then maybe you want to actually say this identifier corresponds to an unsigned integer. Or maybe that this number could be negative at some point later, in which case you want it to be, what, signed or unsigned? If you want it to be negative in the future. It's signed, right, because every negative number is signed. But depending on what types of integers you're going to be dealing with, you may want to choose one of these different types of integers. So what's the difference between these? The difference is how much storage is given to the integer. So the one that you're pretty much always going to be okay with, unless in some other circumstances, is int. So int corresponds to 32 bits. Okay? So int by itself is 32 bits on most computers. Some computers, it has more. I don't know of any that have less than 32, but very commonly it has 32. And then, so what's the difference between int and the other three here? The difference is that short int has at most the number of bits that int does. Sometimes it has the same number, sometimes it has half as many bits as int. Long int is usually either the same or twice as much, and long is either twice as much or the same. It depends on the machine that you're actually working with. So if before you actually start using these, make sure to know how many bits they actually store. So let's just do a quick exercise. Oops. Probably don't need to see my research stuff. Okay, so let's say that int has 32 bits. How many bytes is that? 4, because how many bits are in a byte? 8. So 32 divided by 8. Okay, well, let's see. If we had n bits of information, remember, how many things could we address using n bits? If you remember back. Not n squared the other way. 2 to the n. So why is that? If we have a whole bunch of data right here, then if I want to choose a bit for this position, how many choices do I have? Well, just a single bit for this position, 0 or 1. So therefore, I have 2 possibilities for that one position. Independently, how many do I have for the second position? 2. So 2 times 2 times 2 times 2. If we have n bits, so we have 2 to the n possible binary numbers I could fit into here. Okay, well, if we have 32 bits right here, then how many pieces of information can I store? Way more than 5. 2 to the 32, which is approximately 4 billion. So if you think about this, so int by itself, if you don't include anything else, is signed by default. Okay? So if I don't say unsigned or anything, int is signed. So this means that I can address 4 billion integers. And how they work is, if you have a signed integer, then roughly half of the integers are allocated to below 0, and half of them are allocated to above 0. Okay? Well, let's see. How do we actually indicate whether a number is negative or not? So if I just have an integer right here, let's just say an integer x is 0, 1, 0, 1, 1, something, whole bunch of other bits, doesn't actually matter. How can you actually tell this number is signed or not? Well, how do you tell the sign? Where's the sign here? Oh, we'll get to that. There actually isn't a sign right here, right? It's just a bunch of data put together. Remember, are computers dumb or smart? Dumb. So if they're just looking at a whole bunch of data, all these bits right here, it can't tell whether something is signed or unsigned unless we actually force a mechanism that allows us to determine whether a number is signed or not. So do I have it here? Yeah. Okay, so we'll get to that. So how do you actually tell whether a number is signed or unsigned? And by you, I mean, how does the computer tell? The way it does it is it allocates 1 bit for the sign. Remember, how many different signs do we need to deal with? Well, we need to deal with positive and negative. Those are 2 possibilities. How many bits can I use to address 2 different things? 1. Do I need 2 bits? No, because that would give me 4, and I only need 2 here. So, in fact, we only need to allocate 1 bit for the sign of the number. And so, how does this actually work? So, for our purposes, we don't care where the sign bit is. It just doesn't matter. But the way it actually is done is this first bit, if it's 0, then it's either 0 or positive. If this first bit is a 1 instead, then this number is negative for sure. Okay, so if this number starts with a 0, then this number is either 0 or positive. If it's 1, it's definitely negative. Well, let's see. Well, if this bit is the only purpose of this bit is for the sign of the number, how many other bits do we have to actually represent the number itself, not the sign? 31. So how many integers can I actually address once I know what the sign is? 2 to the 31. Good. So that means that an integer's range is between, so this is approximate, not exact. It's between 2 to the negative 31 and positive 2 to the 31. Okay? So that is how signed integers can be represented. If we were dealing with a long integer, for example, let's suppose that it has 64 bits to work with. Then the range of that would be negative 2 to the 63 to positive 2 to the 63, roughly. Okay? What if we were dealing with an unsigned int? So this number is definitely not going to be negative anymore. Well, do I need this signed bit anymore for an unsigned integer? No, I don't need it. So let's see. For an unsigned int, what is the smallest value an unsigned int can have then? It can't be negative. 0, right? I can represent 0 just fine, just a bunch of zeros put together. Well, what is the upper bound then? How many bits of information do I have to actually concern the actual number, not any sign bit anymore? How many bits do I have? I have 32. So in fact, the upper range of unsigned int is 2 to the 32. So the vast majority of the time, if your integers that you're dealing with live in here, might as well just use a normal signed int. If you really need the range between 2 to 31 and 2 to 32, then an unsigned int is a good option for you. But why would I ever use an unsigned int, even if my integers are all really small, let's say between 0 and 100? Why would I prefer an unsigned int over a normal int? Because I could use either one for this scenario. Why would I prefer unsigned? Remember, the computer doesn't care, right? Because the integers are small enough. Yeah.
So like, does the signed int like take up more space?
Nope, they take this exact same number of bits.
Okay.
So there's not a memory thing here. Yeah, it's easier to work with. And if the programmer writes unsigned int instead of just normal int, what does that communicate to the person reading it? Okay, can this number ever become negative? No. So then they get some information about what you're trying to say in your code. If you put unsigned int, then you know for sure that it can never be negative. But if the number could be negative and I put unsigned int, is this an error? An error in some sense. Yeah, there's something that went wrong there. Okay, so the rest of the bits are for data, as I just said. If you never need negative numbers, always just choose unsigned. Even if you don't need the full range, it's just easier to understand and work with. A variable is signed unless you explicitly put unsigned. So it's signed by default because most people need the sign in most of the cases, but sometimes you do need unsigned. So it's there for you. Okay, so remember when I talked about the types of integers, I said that there are these things, short int, just normal int, long int, and long int. You could actually ignore the int part other than just the integer itself. So you can actually do these types of things. So instead of saying short int temperatures, you can just say short, and it's much shorter that way. If you want to say have a long int and have it be unsigned, you can just put unsigned long and you're all set. But for int, you actually have to put int there. Any questions on how integers in general work? So I'm not going to test you on like the differences between these. I maybe would ask about like if we had some strange integer data type that has this many bits, how many what's the range on this weird integer type that I give you? So like if it was 48 bits, for example, instead of 32, then the range for signed would be between -2 to the 47 and +2 to the 47, right? Because 1 bit is for the sign. Any questions on how, yeah?
Like the number 32.
Mm-hmm.
How many bits are?
Right, so if we wanted to store, so that's actually a great question, a great test question, by the way. If I have the integer 32, and let's just say that we're dealing with unsigned data, okay? So we have an unsigned integer, and we want to store 32 in that into that type. Want to store 32 into n bits, unsigned in this case. How many bits of information do I need for that to happen? Any guesses? 8 is a good guess. Any other guesses? Any lower or higher guesses? 5, another guess. Other guesses? 2 bits? Is that okay? 2 bits. Any other guesses? It's actually 6. It's 6 bits. Why is it 6 bits? Let's see. Well, what is the range on 8? 8 bits. So it's roughly -2 to the 56 and be between 2 to the 50. It's actually 255 in this case. So could I do better than 8 bits to store just 32, not worrying about any other value? Yeah, I can do better. So 8 is actually not enough. What about 5? Well, what is the highest value that I can store in 5 bits? Well, it's when I put a 1, 1, 1, 1, 1, right? That's the best I can possibly do with 5 bits. What is this in decimal? Well, let's see. This is the 1's place. And then here's the 2's place, 4's, 8's, and 16's. So 1 plus 2 plus 4 plus 8 plus 16 is, anyone who could do math quickly in their head? 31. So the highest thing I can store with 5 bits is 31. So how many bits do I actually need? 6. Do 6 bits suffice? Could I actually represent 32 with 6 bits? Yeah, well, what's the decimal number of, what's the binary form of 32 with 6 bits? 1, 0, 0, 0, 0, 0, right? And in fact, you can actually verify this, because if you just add 1 to this number and then just do the arithmetic and keep the carry along the way, then we'll have an extra carry once I process the first 5, and then I'll have a 1 extra on the front. And so this is actually the binary form of 32. You actually picked a good value because it's right on the border between one number of bits and the next one. That's also a good question, yeah.
From where did you get -256?
What's sorry?
-256.
-256? What about? Sorry. Yeah. So this was. Yeah, I was completely wrong there. Because we put unsigned, this has to be from 0 to 255. You're right. Yeah, that was my mistake. But it's still 255 because 8 bits can only represent 2 to the 8 things, which is 256. So it's 0 through 255. Yeah.
A bit's always read from like the biggest on the left, like 120 on the left and 0, 1 on the right.
A great question. So the question is, are bits read from left to right or right to left? So this is a very controversial thing. So the actual terminology for that is something called endianness of data. So whether data on a computer is read from left to right or right to left depends on the actual architecture that you're working with. The vast majority of your computers are read from left to right, just like a normal number. So the most important bit is the one on the left, which is the one on the bottom number here. And then the least important bit is the one on the right. So the 32's place in this number, the second one, is the one on the left, not on the right. Just like how you read numbers normally. But just be aware that some computers do the exact opposite. And that's caused headaches for many people in dealing with both of them at the same time. Any other questions about ints? Okay, so then let's go on to literals. So this one is not that important, but it is just here for completeness. So if you want to actually put an integer into a different data type other than actually just an int, then what you would do is you would put this literal identifier on the end. So this says that 234, the literal itself, 234, just that is an int, int. But if I want to put it into a long variable, then what you would do is you would put a capital L on the end. In fact, this is actually not necessary, but it's just for readability. So if you just put 234 and a long on the left side, it in fact does the conversion from int to long automatically for you. You don't have to worry about that. But it's just there to signify I explicitly want this to be a long data type. And the reason for that is you said long on the left side, so the thing on the right should be stored into a long because we're assigning from right to left. So we don't actually have to worry about this. But if you want to have it for readability, then I recommend doing so. If you want to put it into a long for a huge data type, then you would put a double L. Okay, so here's an interesting one. So sometimes if you're working with actual memory addresses in a computer, you don't want to actually have to write the binary memory address like 0110000 or etc. But it's actually really useful sometimes to work with something related to that binary form, but not have to write the entire address out because that's just way too long to reason about. So what people usually work with, especially in the security domain, are different bases. Okay, so instead of base 10 or base 2, they work with a base that's a power of 2. Okay, so what happens here is they're basically just compressing the number, and we'll see how to do that. They're compressing the number into a form that's more readable, but it still it contains exactly the same information. So I don't have to do a weird conversion between base 2 and base 10. If I work with a power of 2, then it's a lot easier to actually convert. And we'll actually see how that works in a second. Okay, so let's actually do an example of that. So let's convert, what's your favorite number? 42? 42. Okay, so what's that in binary? 1, 0. Let's do it in my head. Yeah. Okay, yeah, that's 42. In binary, I'm actually going to duplicate the number. So I have no idea what this number actually is. It's going to be way large. It's 2 to the... Yeah, I can't think of it in my head. Okay, so let's look at this number. So how many bits are in this number right now? 12. And it actually, your suggestion of 42 is great because, and we'll see in a second why that is. So let's say that we want to work with base 8 for whatever reason. So base 8, what you do is, so I'm going to copy the number down here. And what I'm going to do is, I'm going to break the number up into chunks of size 3. Okay? So I have to work from right to left on this, but since it's 12 bits, it doesn't actually matter. So what I'm going to do is I'm going to break this number up into chunks of size 3. Okay? Because we're working with base 8, and 8 is 2 to the power 3. So the 3 is why we break it up into 3's here. So what we're going to do now is look at each chunk, and we're going to convert that to, in this case, decimal. Okay, so what is 101 in decimal? 5. So this one's 5. What is 010 in decimal? 2. And then you can actually see that the other ones are also 5 and 2 because it's literally the same thing again. So the octal number for here would be, well, octal always starts with 0, meaning that it's indicating that this number is an octal. The 0 is not part of the number. It's just to indicate that it's in octal, in base 8. So here it would be 0 to say it's an octal, 5252. So that would be the conversion from 42 copied again, whatever that is, and then convert that to base 8. What about base 16? So if we broke things up into size 3 for base 8, what should we do for base 16? 4. So that's why it's useful that this number has 12 bits, because 3 and 4 both divide 12. So we're going to break this number up into chunks of size 4. Well, they're all the same number. Okay, so this is actually interesting. What is this number 1010 in decimal? 10. Is that representable by a single digit in decimal? No, it's 10. Does anyone know how things are stored in actual decimal past 9? So in hexadecimal, what has happened is we want to store things like this in these numbers, but how many possible things could be stored in a single hexadecimal value in each position? Well, we have 4 bits to work with. How many things can I store with 4 bits? 16. How many things have I written so far? 10. So I have 6 to work with, and I don't have any other digits left. So what actually happens is that they start using letters. So they do the first 6 letters like this. So here in hexadecimal, capital A represents 10 in decimal. Capital B represents 11. C is 12. D is 13. E is 14, I think. F is 15. Okay? So this number right here is what we just described as 10. So what is 10 in hexadecimal? Is capital A. And fortunately, the other two are literally the same. So this number is shouting at us. So then the hex form of this number is, well, it tells us to, I can't just put 0 on the front because that indicates it's in base what? Base 8. So the way that it's done is that they put 0x to indicate hexadecimal. Okay? And then I would put AAA. So if I want to store whatever this number is in hexadecimal, you can see it's a lot shorter to write that than the 12-bit number that we had before. So again, this is not really that important, but if you encounter this sort of thing, it's just a good idea to understand when something is in base 2, base 10, base 8, and base 16 are the usual formats. Yeah?
So when would you be writing octal or hexadecimal or binary in your code?
It's very, very, so the question is, when would you actually write this in your code? The answer is very, very rarely. But the important thing to note is if you actually see this sort of thing, especially if you're going to be working in security, then you will see this a lot in that domain. So it's just a good idea to understand how things are actually done. Okay, yeah?
I don't know how to find the decimal. Like 5.
So converting to decimal is going to be actually a little bit harder because 10 is not a power of 2, so I can't just break this number up into chunks. So what you would have to do is that this number in decimal is, well, this is 2, this is 8, this is 32, 128, 512, and 2048. Add those numbers up, and then you'll get the decimal number. Good job. Faster than I can do it in my head.
I don't quite understand what like purpose of this is, and like what it means by splitting. So you can
The question of every engineer, right? What is the purpose of this? All this is just a compact way of writing binary. That's all it is. It's just if you want to actually write a binary number, some number in binary without having to convert it to decimal, you could write it in the decimal form, and there's a way to do that in C++, but the far easier way is to convert it to hexadecimal or octal and then just write that in your code.
It's another like type of binary.
It's not another type, it's just another way of writing it. And it's just much easier and much more compact to write than just writing the whole binary number.
How do you decide like it says base 8, but how do you decide to split it to 4?
Because base 16, that's 2 to the power 4. So that means that each position in the hexadecimal representation can represent 16 things of data. Well, in binary, how many bits do I need to get to 16 elements of data, which is 4.
So 2 and 4 is
Right. So if I wanted to work with base 32, for instance, then I would break it up into chunks of size 5. 64 chunks of size 6. Okay? Yeah.
For the first, second example, how it works, the decimal number step.
Because for 1010 in binary, this is 2 plus 8. If you just look at the powers of 2 from left to right, this is 1, this is 2, the third one is 4, and the fourth one is 8. And then when there's a 1, you consider that number. So I don't consider 1 right here, but I do consider 2 because there's a 1 there. I don't consider 4, but I do consider 8 because there's a 1 there. And so it gives us 10 because it's 8 plus 2. Other questions? So this is not that important, okay? This is just for completeness. But you may encounter this sort of thing.
Don't use hexadecimal designators for colors in a lot of different coding languages.
Yes, but it's just that if we're not going to be dealing with colors here. Yeah. Yeah, because those use 8 bits of information usually. Because they can store 256 things, but we're not going to deal with that. Okay, well, if we're not going to be dealing with just integers, what thing might you want to have? So if you want to have some fractional part of the number, are integers a good way to do that? If you want, no, so you want something else. You want something that's called floating point, okay? So floating point, all it is just an extension of the integers to where you can hold a decimal part as well. So if your data needs the decimal part after the number, after the decimal point, then floating point numbers are a good way to go. And integers are not the way to go for that. So if you wanted 12.45 or negative 3.8, floating point is a great way to go. Okay, so I'm not going to test you on how these are actually stored because it's actually much more complicated than the way integers are stored. They're stored essentially like scientific notation. So remember, scientific notation is some number times some base to some power. It's stored something like that. Not exactly that, but very close to that. All floating point values are signed. There's no such thing as an unsigned floating point because of that reasoning and the way that they're stored internally. The ones that we'll be dealing with are floats, doubles, and something called a long double. The vast majority of the time, because the ranges on all three are just so enormous, the vast majority of the time, we'll be working with double here. Because the memory constraint that they have is that float is 32 bits, double is 64. So we don't really need the range aspect anymore. So the only real difference that would matter to anyone here is the amount of data that they use. But since we have so much data in our computers anyway, 32 bits versus 64 bits is probably not going to cause a huge problem for us. So the vast majority of the time, just use double. It's far easier. But sometimes you'll see an actual floating around in some people's code. So just note that there is a difference between them, but the vast majority of the time we'll be using double because it's just much easier to work with and most people understand how it works. So the size of the float is at most the size of whatever this double thing is. As indicated by the name, the vast majority of the time a double has twice the size of a float, has double the amount of size of the float, but we're not going to really worry about that. And then the long double has at least as much, but usually twice as much. Depends on the architecture. Okay, so you can either store the number just like this. If you just want to write it in your code, you can represent 10 pi roughly like this, or 3/8 times 10 to the negative 5, something like this, just the actual number itself. Or you can actually use scientific notation. So the top one and the one right below it, they're both exactly the same. It's just sometimes the scientific notation is easier to read. That's the only real difference. You can do capital E, lowercase e. We're not actually going to deal with this, but it's just something you might actually see sometimes. Everything is double by default. So if you write any one of these 4 values, they're doubles by default. But sometimes if you want to actually force it to be a float for, I don't know why you would want to, but if you do, then you would put, instead of L on the end, you put F. Okay, so that would indicate floating point, or float in this case. If you want it to be a long double, put an L on the end, but again, double has so much range that you're not going to even care about having to use long double or not. Okay, so then you may be wondering, okay, well, what if I tried this? Actually, let's do an example. So let's actually code up an entire little assignment by our boss here. So our boss says, I want you to implement the Pythagorean formula for us. Okay, so maybe we're trying to do some calculation, implement the Pythagorean formula for us. And by this we mean, let's see. So remember, what is the Pythagorean formula? It's a squared plus b squared equals c squared. So in this case, what we're going to do is we're going to input a and b, and then we want to output c. So not c squared, we want to output c, and the positive one. So in this case, c could be negative because of the squaring, but we're not going to deal with the negative root of this equation. So let's see. So if I want to write c equals something, how is it in relation to the rest of the formula up here? Yeah, something you learned at some point or another. It's the square root of a squared plus b squared. Okay? So let's see. Would it make sense for us? So integers obviously make sense to input as input here. Would it make sense for a user to input a floating point value? So a float or a double, the same thing. Would it make sense to have them have a non-fractional part, a fractional part of the number? Possibly, yeah. So in this case, it actually makes sense to have a input that's not exactly an integer. So we should be inputting, instead of ints, we should be inputting what type?
Double.
A double. Okay, so if we want to get input from the user, what things do we need to actually put in our code for it to actually work? Well, C out, C in, and what thing do we need to have that to make it work? IOStream. So we need to include IOStream. And then this line of code, my least favorite line of code ever, and I'll explain at some point what it does. Then we have this int main, which is where our code goes. So I want to input A and B. So what types do we want A and B to be? Double. So then we are going to have them be doubles, A and B. So maybe we want to prompt the user. So let's just say cout enter A and B, just as an example. And then now I want to actually input the two values A and B. So what do I do? Cin. So do I do Cin this way? Oh, the other way. You can tell by my tone of voice, right? So what is a shorthand for inputting both values at the same time? Yeah, another instance of this. So I could have done Cin A, and then the next statement is Cin B, but this is just a shorthand. Okay, so we want to actually calculate this value now. We'll get to square root in a second. But think about C. We want to calculate the value for C. What type should it have? Should it be an integer type or should it be a floating point type? Floating point, because the vast majority of the time, when you do square root, it's not going to be actually an integer, right? So then we want C to be a double, right? Or float, it doesn't matter here, but we're going to use double here because it's not always going to be an integer. So then we'll figure out how to do square root in a second. So we'll do square root in a second. But how do I figure out what a squared is? A times a. So that's actually pretty simple. A times a plus, I think now it's b times b. And then once we're done, what do we want to do with the value of c? I'll put it to the user because they may want to know what is the root to this equation. So then maybe we'll say that the value of c is, and then c at the very end. And then maybe a new line to make it nicer to print. So let's just make sure that it actually works before we figure out how to do square root. So what do I have to do with the code? I haven't compiled yet. G++, and then the name of the file is main in this case. And then I got to run a.out. So let's enter a and b. What are some values for a and b? 5 and 4. So then the value of c, well, this is obviously not the right value, but it actually works. Why? What is 5 squared plus 4 squared? Well, it's 25 plus 16, that's 41, so it works here. Okay, so then now we got to figure out how does square root actually work? Have I covered how the square root function yet? No. So what happens here is I can't cover the entire C++ language because we would be literally here for years if I wanted to do that. So if you are tasked to use some functionality like square root, what should you do? What you should do is look up the C++ documentation or examples online. And then once you find those, what should you do? Cite them in your code. So let's look up on the web. So let's look up C++ square root. I should not have square root there, but okay, so I see this example up here. And then, so let's look at the information that it gives us. So we haven't covered all of this information, and you may not be able to read all of this, but let's try to discern what happens. Okay, so we see this thing in angle brackets up here. What are those things called that are in angle brackets? It's some kind of preprocessor directive. Okay, well, it says that it's in the cmath, whatever that is, header or directive. And so maybe we need to include that directive at some point. Okay, so that's fine. So the function is called sqrt, and then the description of it says it returns the square root of x. Okay? So I don't well, I do, but you may not understand this notation up here, whatever this is. So maybe let's come down to an example. So it says that we have a double param and result up here. And then we have, we're setting a value to param, and then it says sqrt with parentheses on param. And then it's being stored in the variable called result. Okay, so then maybe what we can do in our code is what? What could we do here? Well, we want the square root of a squared plus b squared, all of it. So what could we do here? SQRT on the front here. So let's actually try to compile this. It might actually work, I'm not sure. Oh, So we tried to use SQRT, but it says, I have no idea what this SQRT thing is. What did we do wrong? We didn't do that directive. What was the name of that directive we should include now? CMath. Good job. So we got to include CMath. So let's actually try to compile again.
Is there any reason to call cmath first?
I'll get to that. There's no reason though. So let's do the same two values from before. And in fact, that's, well, is this what we should expect? Well, let's actually confirm. So we want to figure out what is the square root of 41. And in fact, if you look here, it's the same values up here. Here's a question for you to think about. Why do we not get all the values here? And what's the square root of 41? Is it rational or irrational? It's irrational. So in fact, we can't actually represent all possible data here. I still have 3 minutes. So we can't represent all data here. So you may have to think about, do I really need all of these digits to represent to the user? Or like in the case of assignment 1, we require you to output 4 digits of precision after the decimal point to get you to think about how to actually work with this. Okay, so this is just a simple example of being able to declare 2 doubles, floating point values, do a prompt and enter the values, do some simple computation, and then print the value out at the end. What if we tried, actually this will never have an issue. So let's see. So let's just say that these are 2 sides of a triangle, an actual triangle. Can the sides of a triangle ever be negative? No. Why does this work? I put the sides of the triangle are -1 and -2. Why does that work? Are computers smart or dumb? They're dumb. Does the computer know that this application is designed to figure out the hypotenuse of a right triangle? No. So if we were to do that, then we would need to do some checks somewhere in here about figuring out, is this value of A that was given to me a good value? Or did the user fall down and hit their head and give us a wrong value? And the similar thing for B. We don't know how to do that yet, but we're going to start adding on different types of checks to be able to figure out, is this data a good piece of data to work with? But for now, this is all we can actually work with. Any questions on this example? I still have 1.5 minutes.
The size difference between a float and a double, like since it's 32 bits, right? Usually.
Yeah. So.
Why is it that you chose this double and not float?
I mentioned this already. So the ranges on them are large enough for which we usually just don't care about the difference between them. The only difference is the size difference. So usually on most computers, a float is 32 bits and a double is 64 bits. But the difference there is only 32 bits, so it actually doesn't really matter the difference between them. So we usually use double. But sometimes you really do need a float. And like in my research, I actually need sometimes to have the smallest representation for the data that I'm working with. And using a float or double actually makes some of my programs either run faster or slower depending on how big the data I'm actually working with is. So sometimes it's useful. Most of the time it actually isn't, won't actually matter. Yeah?
I just also had a question. When you're doing the square root a times a plus b times b, How does the order of operations, would it ever affect
Excellent question. We'll get to that next time.
it?
I'll see you all on Friday.